Give now a small example of how to use this filtering, but then in the Fourier domain. It's very simple, but you just see in a few clicks how this works. And it's called dither removal. We saw before dither, that is the pointing of real black and real white pixels by a laser printer or any printer who cannot print gray values. You don't see any dithering in this image. It's quite a big image. It is 1000 by 3000. It's called the pixels of the data. It's a tiger, the tiger.gif image. If you zoom in on a very tiny image and you call that sub-image, you see very nicely the dithering. And we want to remove the dithering by looking in the Fourier domain. And let's take a manipulate function. And with this function, you can pick out any row and column and move the image to your liking. And let's say we put it on the face. And we have this face on the tiger. And we take it as a sub-image, 450 by 450. And that's the image we're going to process. Well, how does it work? You simply take the Fourier transform of this sub-image. And let's have a look at this Fourier transform. This is how the two-dimensional Fourier transform of this image looks like. And what do we see? Lots of spatial frequencies. We see spatial frequencies in X and spatial frequencies in Y. So this is the X as spatial frequency. It goes to really high spatial frequency, and here it is to Y. Well, where's the origin of this picture? That's right here, not in the center. Mostly you depict it in the center. But all computer programs give it in the lower bottom. So C++, Python, etc. So you have to take care of it. So the main stuff of the tiger is right here, because here are the lower frequencies. But we have, actually, this is a shifted view. Why people put it normally in the middle, because if you move this whole picture half to the right, we know that the Fourier transform is periodic. So the Fourier transform is the same, and the same, and the same. It's a periodic function, so you can tile the whole space with this Fourier graph. So actually what I see here is what I actually should see here to the left. So if I move this center to the middle, I see a whole circular array of all my spatial frequencies. And that's exactly what I want. So this corner, that's my tiger. And all the other junk here is high frequencies due to artifacts. Of course, due to the dithering. So I have these really high frequencies. So it's very simple what I need to do. I need to filter out only those and get rid of all this. So I make a Gaussian filter that leaves this in and makes this 0. So I go now convolve with a Gaussian, and I make a Gaussian. Looks a little bit complex that I use compile here, and it's a clever way of doing it fast. And let's make an array plot of the mask. So this is my Gaussian mask. And now I want to apply this in the Fourier transform. So if I now make the mask to the corners, so now I have the mask here in the corners. It's exactly the same, but I shifted over half my image width. What I now do is that if I see the I take the mask here, and I take the Fourier transform of the function here. This is what I do. You remember that convolution in the spatial domain is multiplication in the Fourier domain. So now I do a multiplication in the Fourier domain. So this space in between is important. It's just the multiplication. So the mask times the FFT, and I take the absolute values. And now I take the plot of this mask with the FFT, and you see, yeah, I have suppressed all these, but not suppressed this enough. I still have some frequencies remaining, because in this, they were so big that even if the Gaussian was very tiny, it survived. So I should make the Gaussian even more tiny. Well, a nice way to make the Gaussian even more tiny is to take the square of a Gaussian. Because if it is 1/1,000,000th, then it becomes 10 to the minus 12. Or if you take to the third power, it becomes 10 to the minus 18. So it really gets small. But those ones, they're close to 1, they're not changed. So if you take the mass to the power of 3, you make the very tiny values of the Gaussian really tiny. And now you plot. You see now they're gone, but I still have kept here my corners. So this is a trick to make the Gaussian blurring, the Gaussian filtering sharper. And now all you have to do is, from this FFT times mass to the third, you take the inverse Fourier. And you call that restored. And now I array plot them both, the sub-image and the restored image. And you nicely see I have removed all the high-frequency artifacts by Gaussian blurring in the Fourier domain. But just to give you a couple of lines of code how this goes. And it works, essentially well. This is what your eye is doing. It blurs if you see a dotted image. You remove, you take the bandwidth of the what is it? Low-pass filtering of the Gaussian. Okay, just a short demo here. We go to the next step and give you some properties of Gaussian derivatives, and then we go apply them. So we go to Gaussian derivatives. They have peculiar properties, and it's good to have an overview of them and see how they work. So I initialize the whole thing. And let's take a look at the Gaussian. So this is the Gaussian. I call that function Gauss. And now I evaluate the spatial derivative of Gauss. And that's by this partial derivative symbol. And this means you take the derivative to x, how many times? N times. And you take it of this function Gauss. And I do it for 0 to 4. Let's see what happens. Okay, if I take the 0 derivative, means I do nothing. So the 0's derivative of a Gaussian is the Gaussian itself. And this is the first order derivative. And it's remarkable that you see, hey, that is the Gaussian itself, but now multiplied by x, and have an extra term here. If I take the second order derivative, I again find the Gaussian, but now times a second order polynomial. The third order derivative is times a third order polynomial. So the derivatives of Gaussians are essentially Gaussians itself multiplied by some polynomial. So it's far easier to calculate them if you know this polynomial than do this symbolic computation, which is mathematically expensive. So if you plot them, let's see how the graphs look like, we get those graphs. So the 0 order derivative, the Gaussian itself. Here we see the first order derivative, nothing special. It goes up, 0, it goes down. This is the second order derivative. You remember this shape, it is the Mexican head function. This is the second order derivative of a Gaussian. The third order derivative, fourth, fifth, sixth, seventh. I can go on like forever. And you see more and more wiggles come. If you take the limit to infinity, you get the sinus function. So you get an infinite number of wiggles. How many zero crossings do I have? Well, for every order 1. So the first order has 1 zero crossings. Here it never comes to 0. Second order has 2 zero crossings, and so on. So let's now take the derivative of the Gaussian. This is the other way to do it. You take the function d for derivative, n times 2x. But you divide the Gaussian out. So let's see what remains. So now I get only these polynomials. Well, these polynomials are called after a guy called Hermite. So they're called the Hermite polynomials. It was a mathematician in France. This is the guy. He's a little bit nasty looking. And he looked at this equation. If you take the derivative of e to the power x squared, you do that times and times and times again. He said it is changing sign. So I have minus 1 to the power of n. And you get these polynomials times the function itself. we saw that it was changing by sign. This guy is minus, plus, minus, plus. So how do we make these Hermite polynomials? Well, there's a function in Mathematica, Hermite h, and that generates the Hermite polynomials. So it's actually very easy. Here you have a table, and here they are. So a very nice way to make very high-order derivatives is make the polynomial, multiply with a Gaussian, and you have it. It's way faster. This is, in particular in Mathematica, it's very easy. So if you now compare, I make a function GD that's called Gaussian derivative. That is my Hermite function times my Gaussian. And I have to go with, in the Hermite function with natural coordinates, as I explained before. So I have my Hermite function here. Which one? Well, the nth one. And now I define this function GD. And let's calculate this function. You see I have here, it's a function, so this is an underscore something, but I call it x. This is the order something, I call it n, and this is the sigma. So if I do it now for x at scale 4, what do I get? I get this function. So the Hermite polynomial times the Gaussian. If you do it symbolically, of course, you do the same. You take the derivative of this Gaussian and then 4 times 2x. You get exactly the same. So it is an easier way to do exactly the same symbolic computation or calculate the Hermite polynomials and use the same Gaussian. If you take the Hermite polynomials, and this is the 7th order Hermite polynomial, and you plot the guy, you see that it is a 7th order polynomial that goes to infinity very fast with the power of 7, and here to plus infinity. So this function is quite ill-behaved. It explodes to the right and explodes to the left. But the Gaussian hull, the Gaussian is so small that it suppresses every polynomial. Even if you take the 1000th order derivative, it goes with x to the power 1000, the Gaussian suppresses it. That's nice. So if you take now this function f multiplied by this e to the minus x squared, you see that it is now well behaved. So the Gaussian is incredibly suppressing the size of this polynomial. So here we see it as the Gaussian itself, and here we see a high-order Gaussian derivative. You see that the Gaussian derivative is not the hull. So it is not touching the tops, which would be the case in Gabor functions. So Gabor functions and Gaussian derivatives are essentially different. They look like each other. They're often modeled for it, but they are not. Gabor functions, they really touch here the function because it's the product of the Gaussian and the sinusoid. But now here you see the function of a Gaussian derivative. This is a pretty high-order derivative, 20th order. And we're going to use 20th order derivatives. We're going to make Taylor expansions with really high-order derivatives. And we can now make them because the Gaussian is a regularizer. Okay, if you see, we saw it before, how fast is the Gaussian going to 0? It is already at 5 millionths. And if you take the limit, of course, it goes to 0. The Hermite functions, if you multiply the Hermite functions with these functions, you see that they are orthogonal functions. And orthogonal functions have a special role in mathematics, and the Hermite function is one of them. I'm not going to talk too much about it. But the Gaussian functions are not orthogonal functions. That means if you take two different ones, it gets to 0. You see, if I take 1 and 2, you get 0, 1 and 3, you get 0, 1 and 4. Only if you take the same, you get the product here, you get the diagonal. But if you take any different functions, they are different. That's called orthogonal. The Gaussians are not. This second with the third one is, but if you take the second with the fourth one, it is not. And also the functions, they integrate not to 1, like we see the Gaussian. The integral was 1, but the Gaussian derivative can take any value. the first order derivative is 0, for example, there's positive and negative area. How do the Gaussian derivatives look like in the Fourier domain? So I plot here the Gaussian, the Fourier transform of the Gaussian. So my function here is Fourier transform. I take the Fourier transform of the first derivative, and I take the Fourier transform of the second derivative. What do we see? This guy we saw before. It is e to the minus sigma square omega square. So this omega square means it's a function of omega. We do not divide by sigma, but multiply by sigma. So this is the regular Fourier transform of the Gaussian. Here, we see the same. This is the same as the zero-order derivative Gaussian, but it has an extra term, minus I omega, if you see. And this also is the same Gaussian, but now it has minus omega square. In general, it means that if you take the Fourier transform of a derivative of a Gaussian, you get n times I omega in front of it. Again, this is a very easy way to calculate it. So you don't have to calculate high-order derivatives. You just say, take the Fourier transform and multiply with how many times I omega you want. So they are like bandpass filters. The maximum of this function, so if you take the first order derivative and you put it to 0, where is this function 0? At omega is square root of n. So let's now plot a function. And it will plot a whole bunch of functions. I'll explain what I plot. You see, this is my Fourier transform. I multiply with my minus I omega n, minus I omega to the power of n. So this guy here, this first term, is the Fourier transform of a nth order Gaussian derivative. And I divide it by the same function, but now omega is square root of n. So that's the maximum. So I normalize all these functions. So they all have maximum 1. And I do this for the first 12 orders. And what do I get? This is the frequency scale. So you see that the derivative of a Gaussian is a bandpass filter. And if you have the bandpass filter, the lowest order, it is this one. And for higher order, you go to higher frequencies. So this is NS1, NS2, NS3, etc. So you see the Gaussian itself is a low-pass filter. The Gaussian derivative is a bandpass filter. If you look at the zero crossings, where are they? We can have a look. These are all the zero crossings. For the first order, it is in the middle. For the second order, it is at sigma is 1 and minus 1. The third order has 3 zero crossings. The fourth order has 4. And you see, if you take higher order zero crossings, the Gaussian derivatives get wider and wider. So high-order Gaussian derivatives are quite wide. You have to take that into account. You cannot say, I stay on the same small space, but you have to get some bigger. And that sometimes leads to problems. Tomorrow we will see how you can actually calculate how high the order derivative can I actually take before I get run into trouble. You have to know that. You cannot take just a 6th-order derivative without taking some measures, because they get bigger without you knowing it. So all of this is meant to get a little bit deeper insight in what are all these kernels, because these are kernels, these Gaussian derivatives, in our vision and in deep learning. What do they actually do, and how do they behave, and how can we control them? Well, people don't know how to calculate exactly all these derivatives, so people have a... if you plot this, people only have approximation formulas, and this square root is approximation formula of one guy, this is another one, this is even more complex. So people have all kinds of approximations. Don't worry about it, just remember they get wider. They also get very much correlated. If I plot 2 high orders, I plot here the 20th order and the 24th order. Well, can you see the differences? There is almost no difference. And that makes sense, because they're all, the one has 20 zero crossings, the other one 24. It's very similar. This also means it doesn't make sense to take these really high-order derivatives. If you have the 20th one, you don't need to calculate the 24th one, because you already have it, more or less. So it's ridiculous to take real high-order derivatives, and vision doesn't take real high-order derivatives, because you get more and more of the same, and that's a waste of energy. So we don't do that. You can nicely calculate how the correlation coefficient between two Gaussian derivatives is. So here we have the derivative, the nth derivative, and here we have the mth derivative, and we normalize them. So we take the derivative square and the derivative square. This is the proper definition of the correlation coefficient. You remember this from statistics class. It is the Pearson correlation coefficient. You integrate one function with the other, and you divide it by the integral of the square times the integral of the square. It is a lot of calculations, which I'll leave you for reading this afternoon. There's a lot of work I will not go through, but you can actually calculate the whole thing. And then you ask Mathematica really to actually do it. You get a gamma function, and if you plot this gamma function, you can nicely see how the different derivatives, if they are the same, it's correlation 1, and it quickly gets down to 0. Okay, I'll leave this a little bit as exotic. And there are approximate Gaussian kernels, so people use other functions, and you will see in the literature other functions as well, not the Gaussian. Sometimes you see a very famous group of papers is by Tony Lindeberg from Stockholm. Written dozens of papers, and he uses the Bessel function. Well, it's not actually really right to take the Gaussian, but sometimes in computer science it is faster to calculate, and you see the difference is hardly noticeable. So in practice you can take them both. We're a little bit more pure in mathematical sense, so we really use the right functions, the Gaussian derivatives, but sometimes you see these Bessel functions. They are specifically called the modified Bessel functions of the first kind. So you may never have heard of them, but now you know they exist, and they look a little bit like the Gaussian. In Mathematica, it's called Bessel I. I skipped this too. If you have higher dimensions, you can have a look at the Gaussian derivative in X. So this is the Gaussian derivative in X, and this is the Gaussian derivative in Y. So now I take a high-order derivative. So this guy is the second-order derivative in X, and the first-order derivative in X. You see that? If I go over the middle, I go down and go up. So here I have only one zero crossing. So in this X direction, I have the first-order derivative, and this Y direction, I have the second-order derivative. I go up, I go down, I go up. So this mixed derivative is another receptive field that we see in V1. It has all these blobs, ups and downs. So these are mixed 2D derivatives. And we have the first order in X, second order in Y, or the third order in Y. You can make any order derivative. So this guy is a third-order derivative, 1 times 2x, 2 times 2y. And you can make them anisotropic. And that's the summary of my Gaussian derivatives. Are there any questions on Gaussian derivatives? Because then I want to spend some time on how to implement all those, and then we go use them. If you implement them, let's say some options. So we go discuss 3 implementations with a Gaussian derivative. First, we take an implementation in the spatial domain with a 2D kernel. Then we take the separable implementation. How do you do that? 1 line X, 1 line in Y. And we take the Fourier domain. It's just to see you a little bit how it is done. In Mathematica, you have this function list_convolve. We saw it in the first lecture. It takes a kernel and it takes a list. Very, very simple. Kernel can be anything. And list_convolve is n-dimensional, so you can take it in 7 dimensions as easy as in 1 dimension. If you look at list_convolve in the help, you see... why don't I get the help? Oh, this is not this is only the text. Anyway, if you see we saw it before. If you take list_convolve and you want to have a look, it has all these nice examples. So you take a very tiny kernel and you take a very tiny image, you see exactly this comes out. So we know exactly what it does. We define the Gaussian function. So we have here, it's the function of x, 1-dimensional. This is sigma. You see it is about the underscore, that's a variable, with the name sigma. And this means with the condition that sigma is larger than 0. And this is my Gaussian. So it's explained with the underscores, I said that before. And now we go make the Gaussian derivative as a plane convolution, GDC. It's a function on an image, n times 2x, n times 2y at the scale sigma. The scale is important. And you have to define the scale. You want to see the edges of the leaves or of the tree. So we make multi-scale derivatives. We always have to implement a sigma here. And of course you will say, well, I want to make sigma really small. I want to make sigma 1/10 of a pixel. We will see what happens if you make sigma really small. You get errors. So let's implement this. We throw away any previous definition by unprotected, and we can now modify it if it were. And here we have the function. This means it is a delayed execution. I don't really make it yet, but when I run it, it is made. It is a subroutine with local variables, x, y, and kernel. And why does it that? It first makes a kernel. It evaluates the derivative of this Gaussian times the other Gaussian, x n times 2x and y n times 2y. And you make a table from y from -4 sigma to +4 sigma, and x from -4 sigma to +4 sigma. You see that the fastest running element in Mathematica always comes at the end. So you first do to y and then to x. It's a little bit you have to think about. And then we take the numerical value. I don't want any symbolic values, so I take n. And then I do the simple thing. I take the list_convolve of the kernel times the image. And this is an extra term. That means, what does the function do when I reach the end? You have to stick with, to deal with the borders. You have to do padding with zeros or something else. We saw it before. Because normally, if you do a convolution, suppose you have 5 pixels here and have 3. This is the first, the second, and that's the third. I got an output image that's smaller than my input image. Well, you don't want that. So normally you want to stick out a little bit over the half, and then you roll up your image. So what is ending here, you take from the rest. So you make it circular, and then you go with these 3. Well, if you want to stick out half of your kernel, and my kernel was 3, you can tell that to Mathematica. So you say you take the kernel to half, take the dimensions of that, and then take the upper round. It's called ceiling. You have ceiling and floor. So if you put a number here that is the upper rounding of half of your dimensions, so half of 3 is 1.5, so you take 2. That means 2 stick out. Then you do this in x and in y. Then you get the same output dimensions as the input dimensions. Okay, it works. And if you now, I'll turn off this. If you now convolve this on, oh, I have to define this guy. And it's all very simple. Now you get an implementation of, you get an image here, and it has an edge going up and an edge going down, and it calculates it. It's not clever, though, because I have a lot of calculations. It is a two-dimensional stupid calculation, and we want to make it more clever. And this is how it goes. We call it the separable implementation. It's called the function GD. It takes an image as a 2D array, as a list, nx differentiation to x, and ny differentiation to y, and it is a function of sigma. I can add, and I hardly ever do, options. And with these options, I can play a little bit extra. In this case, I use the options to change how I sample the Gaussian, but forget about the options right now. It's a subroutine, which we call a module, with local variables. And now I say I'm going to go from -6 sigma to +6 sigma, so I define it here. I can play with it later. I first make the x array, kx. It's a table of the derivative of the Gaussian to x only. So this is a one-dimensional array, a short array, and x runs from 6 times sigma to from -6 sigma to +6 sigma. So I have 13 values, and that's my little array, the sampling of the Gaussian in the x direction. The y array is exactly the same. So if nx is ny, I have already the derivative to x or ny. I don't have to do anything because I have it already, so then I just take a copy of kx. If nx is not ny, I need a different sampling. I make it again, but now I sample the Gaussian. So I make 13 values for the Gaussian. Then I calculate how much should be the overlap. I call that mid. That is the length divided by 2 and the ceiling. And now we get it. I take the list convolve here from my one-dimensional filter, but I make it two-dimensional by putting extra brackets on it. So this one ray is now a matrix with one row. That's different from a vector. So it is now a matrix. I do the convolution with the image. This is for the shifting the padding at the x direction and in the y direction. But then I flip my image. So I have now a convolution done by all the rows in the x direction. Then I flip my image. I rotate it 90 degrees. I do it with transpose. So temp is the transpose, is the 90 degrees flipped image that is only horizontally convolved in the x direction. Then I take temp, and I convolve it with this filter ky, with the padding, do a list convolve, and then I transpose it again, I flip it back. Well, this turns out to be way faster than the previous one. And it's a task for you to calculate how much faster. Just run absolute timing or timing, and you can see what happens on different images. But you can see that you can easily get 20 times faster by using this simple trick. Take a one-dimensional array in x, a one-dimensional array in y. They're very short, and they run like crazy. So this convolution can be done in milliseconds. It's quite nice, because it's so fast of the separability. So we're going to use this function GD a lot. It is called the Gaussian derivative. So it is D, but then with a G in front of it for Gaussian. So if you take any image now of a circle and you define this function GD and you plot it, you get nicely this function. Okay, you can do this in 2D, in 3D, in 4D by just repeating this whole thing. You just make kx, ky, kz, etc. You can make it as high dimensional as you want, but it is essentially each time a 1D convolution. If you have some examples which are nice, what happens if I take an image of a spike? So I calculate this image, and if I do an array plot of this image spike, it's a very simple image. It has a single pixel wide. What happens if you take a convolution with a kernel with a spike image? It is the sampling function in 2D. It's exactly the delta function. It picks out exactly, you get your filter back. So this is a very nice way. So if I plot now this function spike, and I take the derivative of, I convolve this function, but now I take a very big scale. I scale 20, so I get a blurred one. You see that I get my filters. So if you want to see your filters that you're working with, and you have calculated some, I don't know, some intricate things, you want to see them, apply these filters on the point image, and you get exactly your what's called point spread function. Well, this is used in any medical image device. If you want to see how blurry is your imaging device, is your ultrasound system really fine-tuning? Is it making sharp images? Your CT scan, is it making sharp images? CT scans do a little bit of blurring. Ultrasound scanners do a little bit of blurring. So what people do in a CT scanner, every 14 days, Philips comes over, and they do it locally. You put a 25 micron copper wire in a CT scan, that's a point, and you make an image. And of course, that image is not a point, but that image is a Gaussian function. And that is the point spread function of that device. So every pixel of the patient is actually blown up with that Gaussian. So that's why you see, that's how blurry my image is. It is the essential way to test how well imaging works. You can do it for your eye, for any device. And you can also do it for these derivatives. If you want to see your kernel, use a point function. In ultrasound, they have these water phantoms, and there's a very tiny wire in there, and you make an image of the wire, and you get what's called the point spread function, and you immediately see the term point spread function. But now we see these Gaussian derivatives, and this is the derivative to x and to y at a certain scale. Of course, if you make the scale very tiny, you make the scale 4, and you calculate the whole thing, you get these very tiny operators. And in vision, we have these very tiny operators in V1, and we have these very big ones. We have a whole range of scales. And we will see later on that we have a nice pinwheel structure. They come at all orientations, they come at all sizes, and they come at all differential order. So we already see some organization in what filters do we have. We still don't know what do we need these high-order derivatives for. This guy is easy, that's just edge detection. It's a template. You measure the difference between two pixels on the x, y, and on the x-axis and here on the y-axis. Well, why do we need second order, or third order, or fourth order? Well, that's coming up next in a few minutes. So, if you take some MR image and you take the pixels out with the command pixel data, and now you calculate, you make a blurred image of this. I take the 0 order to x and the 0 order to y. So if we take 0, 0, this means it's derivative, but it is no derivative because I don't take any order. This is only blurring with sigma 3. Then you get this guy. If you plot it as a height landscape, you see this. It's a very smooth landscape already. So blurring smoothes the whole thing. And of course, you can manipulate this and so on. Well, here we have the gradient. So if you take an image with a CT scan, any image you can put in your own image, you take out the data, and you calculate the gradient, you get images like this. Why is this so low contrast? What do you think? Normally, every display program, if it is in Python, C++, Mathematica, it takes the maximum in the image and it takes the minimum, and put that on white and this on black. That's simple. If your images are very tiny, it just always gives the full scale. The trick here is that you have these very high contrast letters in the image. So this guy is really high, and that ruins your whole picture. Just think about it. It's as stupid as you can think, but you have to see it once and now you know it forever. If you have some artifacts, sometimes you have an X-ray which people have coins in their pockets, and you get very steep edges around their coins. The rest is invisible. Yeah, stupid because of these coins. So you can, of course, change this, and you can change the what's called the plot range. If you want to see the plot range from 0 to whatever, and if you change automatically the plot range. It is just how any contrast and brightness on a screen is regulated. It is nothing else than it gives you the range of intensities over which the mapping is done from your pixel values to intensity values. That's all. So now you see the whole thing. You can even use histogram equalization. I'm not going to explain this right now, but if you use this function, histogram equalization, it fully does automatically expand every region to the full scale, but it is in this case a little bit exaggerated because the background is also having some very tiny noisy things, is also now expanded. So, okay, let's go to some this is an example of an image at different resolutions. I saw that before. So at fine resolution, you see the fine details, and at the coarse resolution, you now nicely see the outlines. If you do this on noise, and suppose you have an image that is very noisy like this, and you do this on a small scale, this scale is 2 pixels, and the next one is 6 pixels, and then 12 pixels, you see that on a very tiny scale, you hardly see the edge. Maybe a little bit here, but that may be due to the noise. If I run this whole thing again and I take other noise, you see it's quite difficult to see. If I take sigma as 1 here, so I do almost no blurring, you see the noise, but our eye can very nicely see the difference. So why can this edge detection not detect it at all? And we can see this. Well, first of all, we use larger scales. And we also use context. And both of them are really strong. And people in computer vision for a long time, they used edge detectors without really realizing the notion of multi-scale. And you see there is hardly anything to detect if you do not take the right scale. So it depends. You have to optimize your scale selection. Later we're going to do this, and we're going to do it first at the coarse scale, and then we zoom in on a fine scale. You can implement this whole guy with n dimensions. So if you have a 3-dimensional CT scan, then you can do x, y, z derivatives. But today we have also 4-dimensional images. So we have MRI of the heart, 3D, 512 to the third, 25 per second. So that's 4D. X, Y, Z, T. So you need high-order derivatives. I implemented this for you. You can use it. It's called GDN for n dimensions. It is actually the whole Gaussian, but it has a simple trick here, the function nest. And the function nest does it multiple times. So if I use this function nest, and I say nest do f on x, do that 5 times, then you see I get f of f of f of f. So now I do a list convolution of x, of y, of z. So I do each time a single convolution. I nest it very cleverly. Don't look at it right now. It is a little bit too condensed, but see this function nest, and you can now take any dimensions and take the derivative. A couple of last things. If you implement this in the Fourier domain, we saw it before. The function is a convolution of your image with your Gaussian derivative. You can go to the Fourier domain. It becomes a capital. So this H becomes H capital, G becomes G capital. This convolution becomes a product. And now I get this function. How do I get my original function? You take the inverse Fourier and you get f. Well, you can do this, of course, also in Mathematica. It's called the GDF, so the GD function in the Fourier domain. You calculate your Gaussian. You say, I take the Fourier transform of the image. I take the Fourier transform of my Gaussian kernel, but I shifted half an image, so the origin of the lower left is now in the middle. And then I do the inverse Fourier. So you see exactly what happens. It is the same as we did with the dithering removal. So you take the Fourier transform of the image, the Fourier transform of your Gaussian derivative kernel. You multiply them, so there's a space here in between. And then you take the inverse Fourier. There are some constants that you need to take care of, and then you go. It works quite well. So if I take an image, I see this is blue, so I forgot to define it. If I now define this function, now you see it is black. It is operational. And now you see I do the Fourier transform. For some reason, I have some very tiny function, probably because this is all zeros, but here is the derivative function. Okay, a couple of last things. How do we deal with boundaries? You see there are some nice boundaries here. This is a famous painter, René Magritte, Belgium guy. Very interesting things. If you take an image like this and you do the convolution, you normally get, because the output size here is the same as there, so my filters stack out, but this was a cyclic convolution, so that means the pixels I needed here to the right, I took them from the left. Well, because this is a ramp, it happens to be that then next door is a very high intensity, a white one, here's a very low, so I artificially, because of my cyclic thing, have a very big jump here. So many times you get, you see the derivative of a ramp is constant, is 0. So it's all 0 here, but I have artifacts here. And you have always artifacts because you do something at the end which you don't want. If you take zeros, yeah, same problem. You can minimize the problem, but there is always a problem. Forget about this problem, just kick away the pixels at the boundary. The vision doesn't have any problem with that because they're very low resolution and they're far out. We don't have sharp pixels at the end. We don't have sharp things. But if you realize that you sometimes have at the edges these strange things, they come because of the cyclic jumps. So people do a lot of tricks. They say we can... this is what cyclic actually does. It repeats the image infinitely in X and in Y, so it does a tiling. I can also say I take an image and I flip every image. So I make every image. So the jump here is always minimum, and the jump here is always minimum, and the jump here too. So I stay in the same intensity. It's just as artificial. It's a little bit less damage, but you always have damage. Okay, that's the last thing. I have some advanced things on speed concerns. If you work with Mathematica, the major thing is that Mathematica is always symbolic. This 4 is a very precise 4. It is the integer 4. So suppose I take the sign of this function, and I make a matrix of this. You see, if I take I is 1 to 4, I divided by a random number, the sign of 1 over 7 is not calculated in Mathematica standard. You have to force it to do it. So you get normally the sign of 1 over 7, and that's internally represented. It's incredibly precise, because this is mathematically precise. If you ever divide by sign over 1 over 7, you exactly kick it out. It has infinite number of decimals. But it's often ridiculous. You don't want that. But MATLAB doesn't have this problem. It doesn't have this luxury. If you now calculate the eigenvalues of this matrix, well, it takes forever. It gives you an incredible number, and you don't want to see all this. This is the eigenvalues of the small matrix, but this is exact, and we don't care. We don't want this. So let's kick out this. If you now take n, that means just take the numerical values, and now you get the matrix. Now this is what we recognize. This is what every C++ and so on does. Mathematica does, of course, exactly the same. Everybody says Mathematica is slow. Well, this is the reason. You forget to make it numbers. And now you do the eigenvalues, and it goes incredibly fast. milliseconds. You can even take a much bigger matrix. So now I take a matrix of 1,000,000 entries. So let's see the matrix, 1,000 by 1,000. And now I do the eigenvalues. In half a second, it takes the eigenvalues of 1,000,000 entries. Well, this is faster than any other program. So that's nice. So you have to think of, if you do this if you do this symbolically, it takes, I don't know, years, if it can calculate it. Memory use is also something important. It remembers everything standard. So if you say, what is previous output number 7? Okay, that happened to be that. What was previous output number 17? It happens to be my, where's my mouse? My point image. Well, it's ridiculous to keep all that. It is handy if you design, but you can, of course, turn this off. And it's called history length. It's a system parameter with $1. If you ask what is history length, it's infinity. Keep everything. If you say history length is 0, it doesn't keep anything, and it doesn't keep all this memory, so you have much more memory to use. These are a couple of small tricks. If you put them in the beginning, you work way faster. Okay, that's it for this second hour. It was just a preparation, a little bit in detail on the Gaussian derivative, and now we're fully equipped to do differential geometry. So now we jump into what happens with first order, second order, third order, and we go do the real thing. So let's have a coffee, prepare, and then we go to invariant structure. Hi.
Ik heb een klein vraagje.